Hello everyone! In this video, I will discuss Chapter 10-1, the scatter plots and correlation. I am Geraldine B. Rufino from Math 3A and the reporter for this Chapter 10-1. Scatter plots and correlation. In simple correlation and regression studies, the researcher collects data on two numerical or quantitative variables to see whether a relationship exists between the variables. We have here an example about if the researcher wishes to see whether there is a relationship between number of hours of study and test scores on an exam. She must select a random sample of students and determine the hours each studied and obtain their grades on exam. We made here a table for the data. So we have in the first column is the student, for the second column is the hours of study, and for the third column is the grades in percent. As stated from the introduction, the two variables for this study are called the independent variable and the dependent variable. The independent variable is the variable in regression that can be controlled or manipulated. So in this case, in our example, the number of hours of study is the independent variable and is designated as the x variable, while the dependent variable is the variable in regression that cannot be controlled or manipulated. In our example, the grade of the student received on the exam is the dependent variable and is designated as the y variable. The reason for this distinction between the variables is that you assume that the grade of the student earns depend on the number of hours the student studied. Also, you assume that, to some extent, the student can regulate or control the number of hours he or she studies for the exam. The determination of x and y variables is not always clear-cut and is sometimes an arbitrary decision. For example, if a researcher studies the effects of age on a person's blood pressure, the researcher can generally assume that age affects blood pressure. So for this example, the variable age can be called the independent variable, and the variable blood pressure can be called the dependent variable. In this example, we can easily decide and know what is dependent and independent variable. While in this example, if a researcher is studying the attitudes of husbands on a certain issue and the attitudes of their wives on the same issue, it is difficult to say which variable is the independent variable and which is the dependent variable. In this study, the researcher can arbitrarily designate the variables as independent and dependent variable. The two variables, the independent and dependent variables, can be plotted on a graph called a scatter plot. The independent variable x is plotted on the horizontal axis, and the dependent variable y is plotted on the vertical axis. Again, a scatter plot is a graph of the ordered pairs x and y of numbers consisting of the independent variable x and the dependent variable y. This is a visual way to describe the nature of the relationship between the independent and dependent variables. The scales of the variables can be different, and the coordinates of the axes are determined by the smallest and largest data values of the variables. So now, I will show you the procedure for drawing a scatter plot using the following example. Let's start with example 10-1, car rental companies. Construct a scatter plot for the data shown for car rental companies in the United States for a recent year. We have here the table. For our first column, we have the company. Our second column, which is the cars in 10,000s, and this is the independent variable. And for the third column, we have the revenue in billions, and this is the dependent variable. For our solution, step 1, draw and label the x and y axis. So we have here, for the x-axis, we have the cars in 10,000s, and for the y-axis, we have the revenue in billions. So for the step 2, plot each point on the graph. So first, in company A, we have in x-axis is equal to 63, and for the y-axis, we have the 7.0, and this is the point. Next, we have for the company B, in x-axis is equal to or is 29, and for the y-axis we have 3.9, and the point is this. Next, we have for the company C, in x-axis is 20.8, and for the y-axis we have 2.1, and the point is this. And for the company D, we have the x-axis is 19.1, and for the y-axis we have 2.8, and this is the point. And for the company E, we have 13.4 as the x-axis, and in y-axis we have 1.4, and this is the point. And for the last, we have the company F, and the x-axis is 8.5, and for the y-axis we have 1.5, and this is the point. So now we have a scatter plot for this example. Next example is 10-2, absences and final grades. Construct a scatter plot for the data obtained in a study on the number of absences and the final grades of 7 randomly selected students from a statistics class. The data are shown here. So we have for the first column is the student, second column is the number of absences or also the independent variable x. And for the third column, we have the final grade in percent, and this is the dependent variable y. So for our solution, we have step 1, draw and label the x and y axis. So we have, for the x-axis, we have the number of absences, and for the y-axis, we have the final grade. For step 2, we have plot each point on the graph. So for student A, the x-axis is 6 and the y-axis is y. And this is the point. For the student B, we have 2 as the x-axis and the y for the y-axis. And this is the point. And for student C, we have 15 as the x-axis and for 43 for the y-axis. And this is the point. Next, for the student D, we have the 9 as the x-axis and 74 in the y-axis. So this is the point. Next, we have student E. The x-axis is 12 and the y-axis is 58. And this is the point. And for student F, we have 5 is in the x-axis and 90 in the y-axis. And this is the point. And for the last student, G, we have 8 as the x-axis and 78 in the y-axis. And this is the point. So now we have a scatter plot for this example. And for the other example, 10-3, exercise and milk consumption. We have construct a scatter plot for the data obtained in a study of the number of hours that 9 people exercise each week and the amount of milk in ounces each person consumes per week. The data are shown. So we have for the column number 1, we have the subject. For column 2, we have the hours, and this is the independent variable x. And for the column 3, we have amount, and this is the dependent variable y. So for our solution, we have draw and label the x and y axis. So for the x-axis, we have hours of exercise, and for the y-axis, we have the ounces of milk. And for the step 2, we have plot each point on the graph. So subject A, we have x is equal to 3 and y is equal to 48. And this is the point. For subject B, we have x is equal to 0 and y is equal to 8, and this is the point. For subject C, we have x is equal to 2 and y is equal to 32, and this is the point. For subject D, we have x is equal to 5 and 64 is the y. So this is the point. Next, we have subject E, x is equal to 8 and y is equal to 10, and this is the point. For subject F, we have x is equal to 5 and y is equal to 32, and this is the point. For subject G, we have x is equal to 10 and y is equal to 56, and this is the point. For subject H, we have x is equal to 2 and y is equal to 72, and this is the point. And for the last subject I, we have x is equal to 1 and y is equal to 48, and this is the point. And we have now a scatter plot for this example. So after the plot is drawn, let's analyze to determine which type of relationship, if any, exists. So in the introduction, we have the two types of relationship, the positive relationship and negative relationship. So for example, 10-1 car rental companies. The scatter plot of the data shown in this figure, it suggests a positive relationship, since as the numbers of cars rented increases, revenue tends to increase also. Next, for example, 10-2, the scatter plot of the data shown in this figure, it suggests a negative relationship, since as the number of absences increases, the final grade decreases. And for example, 10-3, exercise and milk consumption. The scatter plot of the data shown in this figure, it shows no specific type of relationship, since no pattern is discernible. It means that wala tayong makitang pattern if it is increases or decreases, not just like in the previous example. We analyze also that in data shown in figures 10-1 and 10-2 also suggests a linear relationship, since the point seems to fit a straight line, although not perfectly. Sometimes a scatter plot, such as the one in figures 10-4, shows a curvilinear relationship between the data. In this situation, the methods shown in this section and in section 10-2 cannot be used. Methods for curvilinear relationship are beyond the scope of this book. So now, let's discuss about correlation. As stated in the introduction, statisticians use a measure called the correlation coefficient to determine the strength of the linear relationship between two variables. There are several types of correlation coefficients, and the one explained in this section is the Pearson product moment correlation coefficient, or also the PPMC, named after statistician Carl Pearson, who pioneered the research in this area. So again, the correlation coefficient computed from the sample measures the strength and direction of a linear relationship between two variables. We have this as the symbol for the sample correlation coefficient, and this symbol is which is a Greek letter called rho for the population correlation coefficient. Let's see this figure, which is the range of values for the correlation coefficient. The range of the correlation coefficient is from -1 to +1. We see here if there is a strong positive linear relationship between the variables, the value of r will be close to +1. If there is a strong negative linear relationship between the variables, the value of r will be close to -1. And if and when there is no linear relationship between the variables, or only a weak relationship, the value of R will be close to 0. Next, let's see the following figure 10-6, which shows the relationship between the correlation coefficients and their corresponding scatter plot. As the value of the correlation coefficient increases from 0 to positive 1, like in figure A, which R is equal to 0.50, figure B, which R is equal to 0.90, and in figure C, which R is equal to 1.00, which means that the data values become closer to an increasingly stronger relationship. Next, as the value of the correlation coefficient decreases from 0 to negative 1, like in figure D, which R is equal to negative 0.50, in figure E, which R is equal to negative 0.90, and in figure F, which R is equal to negative 1.00, which means the data values also become closer to a straight line, and this also suggests a stronger relationship. There are several ways to compute the value of the correlation coefficient. One method is to use this formula for the correlation coefficient R, where n is the number of data pairs. Take note this rounding rule for the correlation coefficient. Round the value of R to 3 decimal places. The formula looks somewhat complicated, but using a table to compute the values, as shown in the following example that I will discuss, makes it somewhat easier to determine the value of R. Now let's see the example 10-4, car rental companies. The data here is from the previous example 10-1, but in this example 10-4, we need to compute the correlation coefficient for the data. So this is the table. For our solution, we should follow these steps. For step 1, make a table. For step 2, find the values of x, y, x squared, and y squared, and place these values in the corresponding columns of the table. And for the step 3, the last step, is substitute in the formula and solve for R. Now let's start with the step 1, make a table, as shown here. So we have here the additional 3 columns for the given data table. In fourth column, we have the xy. In the fifth column, we have x squared. And the last column is y squared. So for the step 2, we need to find the values of xy, x squared, and y squared, and place these values in the corresponding columns of the table. So first, we need to find the xy. It is the product of x and y, or car x times the income y. So for company A, we have 63 times 7.0 is equal to 441. 29 times 3.9 is equal to 113.1. 20.8 times 2.1 is equal to 43.68. 19.1 times 2.8 is equal to 53.48. 13.4 times 1.4 is equal to 18.76. And for the company F, we have 8.5 times 1.5 is equal to 2.75. Next is for the x squared. It is only the squared of x, so our x here is the second column, or the cars, in 10,000s. So 63 squared is equal to 3,968. 29 squared is equal to 841. 20.8 squared is equal to 432.64. 19.1 squared is equal to 364.81. 13.4 squared is equal to 179.56. And 8.5 squared is equal to 72.25. And for the last column, we have y squared. It is only the squared of y. And the y here is the income in billions. So 7.0 squared is equal to 49. 3.9 squared is equal to 15.21. 2.1 squared is equal to 4.41. 2.8 squared is equal to 7.84. 1.4 squared is equal to 1.96. And 1.5 squared is equal to 2.25. And we complete the table. After we complete the table, let's now find the sum of x, y, xy, x squared, and y squared. So for the x, we have the summation of x is equal to 153.8. Summation of y is equal to 18.7. Summation of xy is equal to 682.77. Summation of x squared is equal to 5,859.26. And summation of y squared is equal to 80.67. For our step 3, substitute in the formula and solve for r. Using the formula for the correlation coefficient r, we have 6 multiplied to 682.77 minus 153.8 multiplied to 18.7 divided by square root of 6 times 5,859.26 minus 153.8 squared multiplied to 6 times 80.67 minus 18.7 squared. And using the calculator and applying the rounding rule, we need to round the value of r to 3 decimal places. So our r is equal to 0.982. And the correlation coefficient suggests a strong relationship between the number of cars a rental agency has and its annual income. So the correlation coefficient suggests a strong relationship because the value of r is close to positive 1. Next example is 10-5, absences and final grades. So compute the value of the correlation coefficient for the data obtained in the subject of the number of absences and the final grade of the 7 students in the statistic class given in example 10-2. So this is the data table. So for our solution, we use again the 3 steps. So let's start with the step 1. Make a table as shown here. So we have additional 3 columns. So the xy, the x squared, and y squared. Step 2. Find the values of xy, x squared, and y squared and place these values in the corresponding columns of the table. So first we have the xy. So xy is only the product of number of absences times the final grade. So we have 6 times 82 is equal to 492. 2 times 86 is equal to 172. 15 times 43 is equal to 645. 9 times 74 is equal to 666. 12 times 58 is equal to 696. And 5 times 90 is equal to 450. 8 times 78 is equal to 624. Next, we have the x squared. It's the square root of x. So we have the x is the number of absences. So 6 squared is equal to 36. 2 squared is equal to 4. 15 squared is equal to 225. 9 squared is equal to 81. 12 squared is equal to 144. 5 squared is equal to 25. And 8 squared is equal to 64. And for the last column, we have the y squared. So it is the square root of y. So the y here is the final grade. So 82 squared is equal to 6,724. 86 squared is equal to 7,396. 43 squared is equal to 1,849. 74 squared is equal to 5,476. 58 squared is equal to 3,364. 90 squared is equal to 8,100. And 78 squared is equal to 6,084. After we complete the table, let's get the sum of x, y, xy, x squared, and y squared. So we have summation of x is equal to 757. Summation of y is equal to 511. Summation of xy is equal to 3,745. summation of x squared is equal to 579, and summation of y squared is equal to 38,993. For our step 3, substitute in the formula and solve for r. So using the formula for the correlation coefficient r, we have 7 multiplied to 3,745 minus 57 multiplied to 511 divided by square root of 7 times 579 minus 57 squared multiplied to 7 times 38,993 minus 511 squared. And using the calculator and applying the rounding rule, we need to round the value of r to 3 decimal places. So we have r is equal to negative 0.944. And the value of r suggests a strong negative relationship between the student final grade and the number of absences a student has. That is, the more absences a student has, the lower of his or her grade. It is a strong negative relationship because the value of r is close to negative 1. Now, let's go to example 10-6. So, exercise and milk consumption. So, compute the value of the correlation coefficient for the data given in example 10-3 for the number of hours a person exercises and the amount of milk a person consumes per week. So, we have the data table here. So, for our solution, we use the 3 steps. So, let's start with the step 1, make a table. So we have the 3 additional column, the xy, x squared, and y squared. So for the step 2, we have find the values of xy, x squared, and y squared and place these values in the corresponding columns of the table. So first is the xy. So we have the 3 times 48 is equal to 144, 0 multiplied to 8 is equal to 0, and so on. Next, we have for the x squared. So the square root of x or the r, so 3 squared is equal to 9, 0 squared is equal to 0, and so on. And for the last column, we have the y squared. So the square root of y, which is the amount, so 48 squared is equal to 2,304, and 8 squared is equal to 64, and so on. So after we complete the table, we need to get the sum. So summation of x is equal to 36, summation of y is equal to 370, summation of xy is equal to 1,520, summation of x squared is equal to 232, and summation of y squared is equal to 19,236. Our step 3, substitute in the formula and solve for r. Using the formula for the correlation coefficient r, we have 9 multiplied to 1,520 minus 36 multiplied to 370 divided by square root of 9 times 232 minus 36 squared multiplied to 9 times 19,236 minus 370 squared. And using the calculator and applying the rounding rule, we need to round the value of r to 3 decimal places. So we have r is equal to 0.067. The value of r indicates a very weak positive relationship between the hours a person exercises and the amount of milk. Now, let's go to the significance of the correlation coefficient. In this part, we answer this question. If when is the value of r due to chance and when does it suggest a significant linear relationship between the variables? Since the value of r is computed from the data obtained from samples, there are two possibilities when r is not equal to 0. The value of r is high enough to conclude that there is a significant linear relationship between the variables, and the value of r is due to chance. The sample correlation coefficient can then be used as an estimator of ρ if the following assumptions are valid. First, the variables x and y are linearly related. Next, the variables are random variables. And third, the two variables have a bivariate normal distribution. A bivariate normal distribution means that for the pairs of x and y, data values, the corresponding y values have a bell-shaped distribution for any given x value, and the x values for any given y value have a bell-shaped distribution. So population correlation coefficient. Population correlation coefficient rho is the correlation computed by using all possible pairs of data values x, y taken from a population. In hypothesis testing, one of these is true. Null hypothesis rho is equal to 0. This null hypothesis means that there is no correlation between the x and y variables in the population. Alternative hypothesis of rho is not equal to 0. This means alternative hypothesis means that there is a significant correlation between the variables in the population. When the null hypothesis is rejected at a specific level, it means that there is a significant difference between the value of r and 0. When the null hypothesis is not rejected, it means that the value of r is not significantly different from 0 and is probably due to chance. To test the significance of the correlation coefficient, we use these three methods, and I will show using the following example. So we have first traditional method, next is p-value method, and the last one is using table I. This is the formula for the t-test for the correlation coefficient. T is equal to r multiplied to the square root of n minus 2 divided by 1 minus r squared, with degrees of freedom equal to n minus 2. Most hypotheses involving the correlation coefficient are two-tailed. If there is no relationship, the value of the correlation coefficient will be 0. Hence, the hypothesis will be null hypothesis of rho is equal to 0 and alternative hypothesis of rho is not equal to 0. You do not have to identify the claim here since the question will always whether there is a significant linear relationship between the variables. The two-tailed critical values are used. These values are found in Table F in Appendix C. Also, when you testing the significance of a correlation coefficient, both variables x and y must come from normally distributed populations. Let's start with the first method, traditional method. So we have here the similar steps like in the previous chapter. For step 1, state the hypothesis. Step 2, find the critical values. Step 3, compute the test value. Step 4, make the decision. And for the step 5, summarize the results. For example, 10-7. Test the significance of the correlation coefficient found in the example 10-4. Use alpha is equal to 0.05 and r is equal to 0.982. Example 10-4 is a car rental company, so we have this data. And for our solution, step 1, state the hypothesis. So null hypothesis, rho is equal to 0, and alternative hypothesis, rho is not equal to 0. So step 2, find the critical values. Our alpha is equal to 0.05 and our degrees of freedom or df is equal to n minus 2. Our n is 6, so 6 minus 2, our degrees of freedom or df is equal to 4. Using table F, first we have our df which is 4 and our alpha in two-tailed test is 0.05 and their intersection is equal to 2.776. And again, it is two-tailed, so we have the critical values, positive, negative 2.776. And in this figure, we have here the critical region, the negative 2.776 and the positive 2.776. For our step 3, compute the test value. So we have r is equal to 0.982, n is equal to 6. So substituting in the formula for the t-test for the correlation coefficient, we have this formula, t is equal to r multiplied to the square root of n minus 2 divided by 1 minus r squared, which is equal to 0.982 multiplied to square root of 6 minus 2 divided by 1 minus 0.982 squared. And our test value is equal to 10.4. So for the step 4, make the decision. So since the test value falls in the critical region, our decision is to reject the null hypothesis. For step 5, summarize the results. So there is a significant relationship between the number of cars a rental agency owns and its annual income. The second method that can be used to test the significance of R is the p-value method. The method is the same as that shown in chapter 8 and 9. It uses the following steps. So step 1, state the hypothesis. For step 2, find the test value. In this case, use the t-test. Step 3, find the p-value. In this case, use table F. Step 4, make the decision. And for the last step 5, summarize the results. For our example, test the significance of the correlation coefficient found in example 10-5. Use alpha is equal to 0.05 and R is equal to negative 0.944. So this is the data table. And for our solution, step 1, state the hypothesis. So our null hypothesis, rho is equal to 0, and alternative hypothesis, rho is not equal to 0. So step 2, find the test value. So we have R is equal to negative 0.944 and N is equal to 7. Using the t-test formula for the correlation coefficient, t is equal to r multiplied to the square root of n minus 2 divided by 1 minus r squared. So we have here t is equal to negative 0.944 multiplied to the square root of 7 minus 2 divided by 1 minus negative 0.944 squared. And our test value is equal to negative 6.398. So for our step 3, find the p-value. So RDF is equal to n minus 2. Our n is equal to 7, so 7 minus 2 is equal to 5. So this is our degrees of freedom. And t is equal to negative 6.398. Using t-test table, let's look for the row with the degrees of freedom of 5. And our t values, in the table, we only have positive values, so let's find for the value of positive 6398. It falls between 5.893 and 6.869. So we have the p-value is greater than 0.001 but less than 0.002. And for the step 4, make the decision. So using the decision rule when using a p-value, since the p-value is less than 0.05, the decision is to reject the null hypothesis. And for the step 5, summarize the results. There is a significant relationship between the number of absences and final grades of the students. The third method of testing the significance of R is to use Table I. The table shows the values of the correlation coefficient that are significant for a specific alpha level and a specific number of degrees of freedom. For our example, 10-8. Using table I, test the significance of the correlation coefficient R is equal to 0.067 obtained in example 10-6 at alpha is equal to 0.01. So we have here the data table. For our solution, we have state the hypothesis. So we have null hypothesis, rho is equal to 0, and alternative hypothesis, rho is not equal to 0. So next, find the critical value using table I. Our alpha is equal to 0.01. Our degrees of freedom or DF is equal to n minus 2. And our n is equal to 9. So 9 minus 2, which is equal to 7. And this is our degrees of freedom or DF. So using table I for the critical values for the PPMC, we have the degrees of freedom is 7 and our alpha is equal to 0.01. and their intersection is 0.798. So the critical values is equal to positive, negative 0.798. Next, make the decision. For a significant relationship, a value of R greater than 0.798 or less than negative 0.798 is needed. Since R is equal to 0.067, the null hypothesis is not rejected. Summarize the result. Therefore, there is not enough evidence to say that there is a significant linear relationship between the exercise and milk consumption. Next, let's discuss about the correlation and causation. Researchers must understand the nature of the linear relationship between the independent variable x and the dependent variable y. When a hypothesis test indicates that a significant linear relationship exists between the variables, researchers must consider the possibilities outlined next. So we have possible relationships between variables. When the null hypothesis has been rejected for a specific alpha value, any of the following 5 possibilities can exist. So first, there is a direct cause and effect relationship between the variables. That is, x causes y. For example, water causes plants to grow, poison causes death, and heat causes ice to melt. Next, there is a reverse cause and effect relationship between the variables. That is, y causes x. For example, suppose a researcher believes excessive coffee consumption causes nervousness, but the researcher fails to consider that the reverse situation may occur. That is, it may be that an extremely nervous person craves coffee to calm his or her nerves. Number 3. The relationship between the variables may be caused by a third variable. For example, if the statistician correlated the number of deaths due to drowning and the number of cans of soft drinks consumed daily during the summer, he or she would probably find a significant relationship. However, the soft drink is not necessarily responsible for the deaths since both variables may be related to heat and humidity. Number 4. There may be complexity of interrelationships among many variables. For example, a researcher may find a significant relationship between students' high school grades and college grades, but there probably are many other variables involved, such as IQ, hours of study, influence of parents, motivation, age, and instructors. Number 5, the relationship may be coincidental. For example, a researcher may be able to find a significant relationship between the increase in the number of people who are exercising and the increase in the number of people who are committing crimes. But common sense dictates that any relationship between these two values may be due to coincidence.